Good evening, everyone, and welcome to Straight Science. Straight Science is an evening seminar series put on by University of Alaska Fairbanks Northwest Campus in Nome and University of Alaska Sea Grant, also of Nome, and you're in the work office tonight. So both UAF Northwest Campus and UAF Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which is the homeland and waters of the Inupiaq, St. Lawrence Island Yupik, and Central Yupik peoples. Now tonight, we are so lucky to have Rick Thoman, and he's going to give us focus in a little bit on Nome. So we're excited about that. And instead of the weather recall and predictions and everything, which we hope you're still planning on doing at some point in the future, Rick is going to bring to us, he's been working with several others on looking at the fall sea ice timing when it arrives, and I believe when it leaves in the spring, and how that is bringing some impacts and changes to Nome regarding our flooding. And who is Rick Thoman, you ask? He is the Alaska climate specialist for the University of Alaska Fairbanks, Alaska Center for Climate Assessment and Policy. No stranger to Straight Science. And he's willing to talk to us tonight on probably what will be later in the wee hours, the Iditarod finish. So we have beautiful weather. It's 15 degrees and sunshiny, calm, which we haven't seen in a long time. Perfect for the Iditarod and perfect for Rick Thoman. So we're so glad you're here, Rick, and bring it to us about our sea ice.
All right. Thanks very much, Gay. Thanks for all of you for joining in. We're a small but mighty group, and we do know that a couple of folks at least have said they would like to hear about this, but there's so much going on tonight in Nome that they couldn't make this, but they'll watch the recording. So we will move right ahead. So this is going to be a presentation, as Gay said, on some work that myself and some of my colleagues here at UAF, which of course is on the traditional and never ceded land of Lower Tanana Dene people, have been working on to basically to put some numbers to things that you probably already know. If you're interested enough to be on Straight Science tonight or watching this on the recording, you already know how sea ice is changing and how that is affecting Nome. In this here, we're going to put some numbers on those changes, and with a particular focus on the coastal flooding risk for Nome. So this is, like I said, this is mostly stuff that you already know, maybe in a little different way, and hopefully as a useful result. So we have this brand new paper. It's soon to be published. It's been accepted in the journal Polar Records, Sea Ice and the Socioeconomic Impacts from Extreme Events in Nome. And Nathan Kettle, Zav Grabinski, John Walsh, and Ryan Owens are my co-authors on this. So here's what we wanted to do. We wanted to take a look at Nome and vicinity. So this is the greater Nome area. We wanted to look at how the interplay between coastal flooding and the timing of sea ice. So what we wanted to do was to catalog impactful coastal flooding or high water events during the time of the year when sea ice, at least historically, could have been present. We wanted to document for impactful events that occurred, what were the sea ice conditions near Nome during those events, and then how is the sea ice seasonality, when there's ice, when there isn't, how is that changing? So that's what we wanted to do with this. Now, the results of this, again, this is going to quantify stuff that you know, but hopefully the outcome of this is a peer-reviewed paper. And so you don't need a peer-reviewed paper to tell you what's going on. But for decision makers, grant writers, having that reference available is going to be potentially useful as the Nome community and the whole region really, prepare and adapt to the changes that we've seen and are coming, and using what's happened, to make an estimate of at least the kind of the near term, the 5 to 10 year future risk as this timing of sea ice can be expected to continue to change. So, as everyone knows, of course, coastal flooding in the Bering Strait region is the single most damaging, highest impact weather and climate event in the region. It's the most costly natural hazard in the state of Alaska, with the asterisk of a big earthquake in Anchorage. So we know the importance of coastal flooding. We know it's episodic, but when it happens, it's a big, big deal. Now, of course, historically, sea ice helped to buffer the coast because there was often sea ice during a significant part of the stormiest time of the year. Bering Sea, of course, is one of the stormiest regions in the world, and the stormiest time of year is the autumn. But historically, sea ice helped to buffer the coast, but of course, that is changing. So, here are some of our questions that we wanted to answer in our paper here. The season, what's the seasonality of impactful storms? You already know this, right? Mostly in autumn. So from a research side, okay, how are we going to document these events? You know it, but we can't really do a mind meld with you, right? We have to have some other way to document it. How's the timing of sea ice development in the fall and the loss in the spring? Has that changed over time? And if so, how much? And then what can we say about the future based on these trends that we see now? At least the 5 to 10 year future. Wouldn't want to use these results for what's going to be the ice, say, at the end of the 21st century. So, coastal storm information. Of course, the number one source of information is lived experience, right? Whether it's from elders, their lived experience, and then what they heard. We have that going back a long way. In recent years, really, post 2010, especially, social media has become a great source for documenting the impacts of coastal storms. So it's great that we have that, but that's pretty short period of record. Nome newspapers, of course, are a major source of information, and they have been mined repeatedly for academic purposes. Here's the top one. There is a paper from 28 years ago that looked at a couple of Nome newspapers back to the gold rush era, to the periodicity of storm surges in the Bering Sea there. So this wasn't really this was not focused on impacts, but rather just when did these events occur. And then a few years ago, myself and some other people there, we also looked at the Nome Nugget, kind of examining the Nugget for any type of weather or climate related impact. So this study was focused on sea ice. That 2020 paper, we looked at any kind of impact. So whether it was, pipes freezing from, really low wind chills, or sea ice, or river flooding, anything that was worthy of a mention in the Nugget, that's what we mined that for. So this one we will be looking for coastal flooding related impacts. And the last source of information that is readily available is this thing called NOAA Storm Data. This product actually started in the first publications in 1950. It didn't contain much in the way of Alaska information, or very episodic, very sporadic, until the mid-90s. Started to become more somewhat more comprehensive at that point. The main purpose of storm data, though, is really for the Weather Service to track and verify or not watches, warnings, and advisories that the Weather Service issues. So it's an excellent source of kind of externally derived information. It's very near real time, and there's not normally much in the way of follow-up. So it's worth a look, but it's not going to have the level of detail that we would get either from newspapers or from people's lived experience. Of course, the Nome-centered expertise is invaluable, and you may have seen Carol Gale's Old Nome Spirit presentation last year at the Western Alaska Interdisciplinary Science Conference that was held in Nome. And so this is actually just a screenshot of a slide from Carol's presentation here, listing some of the really high impact storms. I think we've convinced her that we probably need to include the September 2005 storm in there as well. But you can see there's she mined many newspaper resources to get this, and it's an absolutely invaluable contribution to understanding coastal flooding in the Nome area, and that pulling together that generations, more than a century of Nome lived experience. So what did we do for our paper? So here's what we did. So we limited our research in the Nugget for 30 years, 1990 to 2020. I guess that's 31 years actually. So we wanted to confine ourselves to this recent period because we wanted it to be really relevant to what's happening today. Once we start to get back into the 1980s or before, infrastructure has changed, different societal aspects have changed. So we kind of use that 1990 for that reason, to keep it reasonably relevant to the way things are today within and around Nome. And we were also looking for events that had community scale impact. So, a storm that washed out, one beach miner's rig. If that's all it did, if that's all that showed up in the Nugget, then we probably we didn't count that. We were looking for larger scale impacts, community-wide impacts. So if something impacted the port, that got counted. Obviously, road washouts or anything like that got counted. And then, so we did this basically the same thing for the Nugget and for that NOAA storm data report. So one thing that we also investigated, so as many of you know, I've been doing this weather forecasting gig in Alaska since the 1980s. And I started to wonder, so could we use just the weather observations at the Nome airport? Could that reveal any impactful events that didn't show up in the Nugget? We certainly have captured all of the big events, right? But were there more moderate events that we could capture just using the airport data? I had this idea because coastal flooding at Nome, there's a very narrow window of wind speeds, wind directions, and durations that come along with coastal flooding. So if we used all those factors, could we pick out, could we find any events just based on that data? The advantage of the weather data, of course, is during our period of interest here, there's 24-hour a day, 365-day a year weather observations available. So we had a lot of information that could maybe help us find some events. So that's what we did. Can we use that Nome Airport weather observations? And the answer is no. We looked at this very closely, and it turns out that most of the time that we had winds in the right direction, the right speeds for the right durations, there was no significant impacts. We couldn't find any in the Nugget. There's nothing in storm data. And since the late 90s, we have access to the Nome tide gauge data, and we couldn't find any. And that, in hindsight, that was actually not surprising, because there's a lot of factors that go into creating a high water event, coastal flooding at Nome. It's not just the wind speeds, it's not just the wind direction, it's not just the duration. There's a lot of factors that all have to come together. So the exact storm track is important. What's been the winds over the northern Bering Sea during a storm and before the storm? We saw that, for instance, in August of last year, when we had many storms and the Bering Sea was just elevated for most of the month. And that contributed to the flooding, not so much at Nome, but down in the Cusco Delta in late August. So a lot of things have to come together, from storm tracks, ambient, the preconditioning of the environment, right down to the timing of tides. If the highest storm surge occurs at low tide, if it's going to be a moderate event, that might be the timing of the tides might make a moderate event into a nothing burger, or vice versa, of course. But just knowing the winds at the Nome airport, having that high resolution hourly data, it was a good idea. It was worth looking at, but we couldn't really get anything out of that as far as identifying additional flood events. So this is what we came up with after going with a fine-tooth comb through the Nugget and the NOAA storm data. We identified 8 events during the time of year when, at least historically, sea ice might have been present. So this is basically October to April is the window we used. We didn't have any springtime community scale events that we found. That's not surprising, of course. Spring is historically, not always recently, but historically is not a stormy time of year. So all the events when sea ice might have been present, at least historically, occurred in the fall. Of course, there are a number of events here that were major coastal floods. We didn't go through 2022, but Murbach would not be on this list because historically sea ice would not have been present in September. Similarly, with the September 2005 flood, which is in our date range here, but historically we wouldn't have, there wouldn't have been sea ice in September, so that got excluded. So that's how we identified the events that we're looking at. We got 8 events in 30 years that met this criteria. 3 of them were part of a federal disaster declaration there. Now, how do we going to know about what sea ice is around Nome? Well, in my dreams, I keep hoping that someday somebody is going to tell me that, hey, I have this ledger here that my grandfather started in the 1940s, and then my father added to it, and then I've added to it, and it's got the dates of when we first saw ice, almost every year since the 1940s. Well, until we have something like that, we have to find other sources. So it turns out that in the historical Weather Bureau and Weather Service record, there are occasionally remarks about sea ice. And this is the observation form from May of 1921. And I boxed in there a remark, May 31st. Bering Sea ice moving west from a lead 3 miles offshore. Shore ice is solid. Okay, what a great observation, right? So we know the last day of May 1921, there was still 3 miles worth of shore-fast ice. But you go to June, we go to the next form, which I don't have here for you, but there's a remark about the ice moving west on June 1st, and then nothing else. And then in the middle of the month, there's a remark about the first ship arrival, but we don't know when the ice went out. Similarly, in the Nome newspapers, there's occasionally remarks about sea ice, but there's nothing comprehensive. So this leaves us with our one source of sea ice information is satellite-derived information. And while satellites were useful for assessing sea ice before, starting in the early 1970s, it's only really in late 1978 that the technology became available in satellites to be able to get an estimate of sea ice, at least the presence or absence of sea ice on a daily or near daily level. And that continues to this day. So here is what we got, and here's part of the problem. So this is a graphic. This is the data set that we use. The graphic just shows the sea ice concentration from the passive microwave satellite derived data. And I colored in here the kind of the lightest off-white color there would be open water with sea ice concentration of 15% or less. And I put this up here specifically to give you an idea of the resolution of this product. You can see how it looks kind of blocky, and that is the scale at which this product is available. It's had this about 15 by 15 square mile blocks since the late 1970s. There is higher resolution, spatial resolution sea ice information now at about 4 by 4 square miles, but that only starts in 2011. Now, the big problem with all of this, whether it's that lower resolution but longer time frame historical data, or the higher resolution but more limited time, is that all of these products have difficulty at the land-sea boundary. And the usual problem is that it winds up showing ice in places where there isn't ice. So that is a consideration in using this in near shore areas. Works pretty well in the open ocean, but near the coast, we have to have some caveats. So I threw this slide in. It might be of interest for this work, and also maybe more generally, since we rely so heavily on sea ice, and sea ice is so important for the Bering Strait region. So how is sea ice measured by satellite? Well, it measures it by detecting the microwave emissions from the Earth's surface. So microwaves are longer wavelengths than we see. They're actually closer to radio waves than what we see with our eyes. And it turns out that the Earth the surface, ocean, land, emits in these wavelengths, and happily these wavelengths are transparent to clouds. That is, they go right through clouds as if they weren't even there. Now, the passive part of passive microwave is that the satellite is not transmitting anything. It's just looking down, and it's seeing these microwaves. It's if its eyes are in this microwave wavelength. And in the microwave, ice, water, and land all look different. So by detecting these, quantifying this, can be this information, which is just electrical signals, right, can be processed on planet Earth back to extract sea ice information. And that's typically expressed as a concentration from 0 being no ice at all to 100 or 1, a fraction. 1 is all ice, and then everything in between is that sea ice concentration. So that's what satellites are doing in an effort and we process it here on Earth to pull that sea ice information from these satellites. So now that you know about resolution and how this data is derived, here's what we did. We took that 45-year record of sea ice. We used data from 1979 through 2022, but knowing that we couldn't be too close to the coast, not within that 15 by 15 square mile because of that land contamination. We had to pull back a little bit offshore. And the dots here show you the three boxes that we wound up using. That's in the stars. And then we looked at some that were farther afield. And it turns out that if we got any closer to Nome inside those dashed boxes, we got too much land contamination. So it was showing ice when there wasn't. How do we know it was showing ice when there wasn't? You know, it would sometimes have ice depicted there, you know, in August or something, with it completely unrealistic. Now, another consideration is, of course, that in the fall, ice starts to form first in eastern Norton Sound, where the water's shallowest. You've got the inflow from the big rivers, so the water is less salty. So the freezing point is higher than open ocean water. And so we did test that, for instance, that easternmost dot there. And the three that are starred wound up giving us the best fit. We actually tested all of the dots there, and those three gave us the best fit for as far as what was happening with the sea ice. Now, this is still, of course, a non-trivial distance offshore of Nome, and I wanted to show you in a little more detail how that worked out. And so what I've got here for you, I've just picked 4 years here. This is from the National Weather Service sea ice concentration analysis. So this is a human-produced product. It uses various data sets, not just one, to get ice. And you can see here, since 2015, you know, there's more detail than, you know, that lower resolution 15 by 15 blocky passive microwave. Overall, in general, the points that we picked look to be representative of what's happening right at Nome, you know, right off the beach, or what you can see from town. This past year, November 21st, 2024, there was maybe some ice floating around according to the Weather Service analysis, but less than 1/10. There was some ice there in Safety Lagoon there in points east, but offshore Nome, pretty clear. Similarly, the year before, you know, right at Nome and a little bit offshore, similar. 2021, you'll recall, that was a cold November. Ice formed kind of like the old days, much earlier than most recent years. And again, the offshore points, a match was pretty high ice concentration by November 21st, both near shore and a little bit beyond. I actually had to dig a little bit, but I did find this example from same date, November 21st, 2015, where there was a bit of a difference. So you can see here in the Weather Service analysis, we're on the bottom right-hand side now, that near to Nome, that we had 7 to 8/10 ice analyzed by the Weather Service, but not far offshore, it very quickly transitioned to open water and then sea ice free. So this kind of difference typically does not last very long. In the fall, it can last longer, sometimes in the spring. But based on this, we had pretty reasonable confidence in picking the points that we did, so that we could use the full 45-ish year record. So here are the results. This is the length of the sea ice season. So you already know sea ice season is getting shorter and Nome. Here's some numbers on it. So between the winter of 1979-80 and the winter of 2021-22, on the bottom of the graphic there, that's the start of the sea ice season. Each blue line is one season, and the black lines are just the trend line. Similarly, on the top, that's the spring, and the black line is the spring trend line. So between 79 and 2021, the typical date for ice at Nome on our three somewhat offshore points has become 15 days later nowadays than it was in the early 1980s. Almost the exact same trend, 16 days earlier now than it was back in the spring of 1980. But if you look closely, you'll see in the fall, there's of course variability around that trend line, but most of the dates are pretty close to it. That's very different than in the spring. You'll see there's more than a few seasons when the blue line is either way below or way above that trend line. And that's what we know, right? The ice in the spring is or in the fall is being very strongly controlled by the rapidly decreasing solar heating. Other things are affecting, of course, as well. But that loss of that solar heating is a big deal. In the spring, we've got plenty of solar heating, but both spring air temperatures and winds during especially May and early June can really impact when the ice clears or starts to significantly break up. And we can, of course, get occasionally those false breakups. Ice will move out, be gone for a day or two, and then move back in. That's why these blue lines actually represent the 5-day average, so that we don't get misled there when get these false freeze-ups or false breakups that only last a day or two. We make it last for 5 or more days. The dates are the first date when we had sea ice concentration less than 15%, or in that open water category. So we've lost about a month of the sea ice season just in this 44-year record here. All right, so that's one way to look at it. Here's another way to look at it. So we were just looking at the length of the season. Now here we break it down by half-month intervals. And I want to spend a little bit of time on this graphic. If you're not used to looking at these, what are called box plots, there's a lot of information here, and it tells a really interesting story. On the bottom line, so the horizontal axis there starts in early October and goes through the middle of June there. And what we see here is that, again, you already know this, right? Just what's the sea ice concentration from late November into April, or at least into the beginning of first half of April, there's not a lot of trend. The blue boxes are the first half of our 44-year record, 1979 to 2000, and the orangest boxes are the second half, so we call that the current period, even though 2001 is starting to get a long time ago now. So we've got the blue, old, the orange, new. The box encompasses 50% of in this case, the ice concentrations. That's on the vertical axis. The bar is the line where half of all the values are above and half are below. And then the whiskers here, part of the diagram here, accounts for most of the outliers, technically defined here. Because the whisker has to end on an observation, some of the whiskers are different lengths, even though the criteria here is the same. But what we see here is that all of the change here is concentrated in basically November into early December in the fall, and basically in May, starting in April, but really in May to early June. That's where the change is really happening. So that was the idea here, to really, okay, let's focus in on where things are changing most rapidly. So now we're looking at just the fall period. So November 1st is over on the left-hand side, going to the end of the year. Same idea here. The blue bars are the historical record. The orange are the 21st century observations. Same idea with the black line is half of the observations above, half below. And now to me, this is really exciting. You can see here the second half of November, the red boxes and the blue boxes really start to diverge. We're getting very big differences here in sea ice concentrations for the 21st century versus the late 20th century. Big differences here starting in mid-November, continuing into the second week of December. By the time we get to later December, then they're getting closer together again. Now I do want to put on, I made this here so that the dots, which are the outliers, the really extreme events, didn't clutter this up because we had so many dates, but that's what it looks like. You can see on these outliers, some of these historical values, late 20th century, even in early November, significant sea ice near Nome. And perhaps that accords with your experience. That has occasionally happened in the 2021 to 2022 era, the modern era. Certainly, there's more of these blue dots in the, say, the first half of November, these really extreme events than in the modern era, but they're not lacking. Similarly, in December, there were a few late 20th century low ice concentrations near Nome. There's more of them in the modern era. But really, it's not quite a random buckshot, but it's not really tightly constrained there with these extreme events. That's what these dots really represent, extreme ice years, high or low. Now, from that information, we were able to derive, okay, when is it likely that Nome will not have significant ice? Here, this is the chance. The red line is the 21st century. The blue line is the late 20th century. The chance that it would be open water offshore of Nome, less than a 15% ice concentration. So in the late 20th century, for both these data sets, we were at about 100% before Halloween. There wasn't going to be significant ice offshore at Nome. Then they start to diverge. And in the late 20th century, by the time we get to about November 17th, there was a 50-50 chance that there would be better than 15% ice concentration in our three dots offshore. Nowadays, or at least in the early 21st century, we've pushed that out now 10 more days. So we can think of this as one measure of the window when there isn't going to be enough ice to materially buffer the coast. In the late 21st century, late 20th century, that was, the middle of November. Now we've pushed it out to the end of November. And now, there's a 25% chance getting to December and not having that ice buffer just offshore there. By the time we get out to before Christmas, then in both these eras we have the ice. But this is really the money window here. This lengthening of the time of year, the stormiest time of year, when Nome cannot count on having that ice buffer. Now, in the lead up to this presentation, saw on our Facebook group folks asking about, okay, well, does sea surface temperatures have anything to do with later ice? Because you already know the ice is coming later, and the answer is, of course it does. This is the 50-year trend in sea surface temperatures for September and October, so right before sea ice could be expected to go to form. And the red colors here, here in eastern Norton Sound, this is an increase there of more than 6 degrees Fahrenheit in the average temperature for those 2 months. We are used to seeing this in the spring because of the discharge of warmer water from the Yukon and the Koyuk and the Unalakleet rivers, all the rivers pouring into here, but that persists into the fall. But everywhere in the northern Bering Sea, 3 degrees Fahrenheit, 1.5 degrees Celsius warming. And of course, up in the Chukchi Sea, huge changes. And this is really important, of course, for getting ice down through the Bering Strait, where the Chukchi Sea really has to pretty much ice over before we're going to get appreciable ice down through the strait. For Nome, of course, the ice typically forms in place or moves in from eastern Norton Sound, and that's why this warming is so important for Nome. But absolutely, warming ocean temperatures in the fall are a major contributor to the later formation of our sea ice. Now, I do want to look at the spring, even though we didn't identify any coastal flood events. The changes in the spring are also interesting. They're not maybe quite as dramatic as the fall. The separation here between the older historical period in blue and the 21st century in red. There is a downward trend for sea ice concentration during most of May. And you can see here, back in the day, back in the late 20th century, you notice these bars are bigger. There was more variability here in the April timeframe. And because this is half of the values, half of those 22 years in there, so this is an appreciable number that are, pretty low here, lower than we've seen in the modern era. But that quickly transitions in May. The red bars are mostly below overall. The blue bars longer, more visibility. But the real interesting thing here to me is these outliers. You can see here, you can get, what year this is, right? So basically no or very little ice in April. So this is 2018 here. There were also in this case, one year here in the historical period that had very low ice. Look what happens though here at the end of the spring melt season in these outliers, these extreme event years. So in the late 21st century, we still had a couple of springs, 1979 to 2020, when the ice conditions, okay, maybe it wasn't like 1906 when people were going out on shore-fast ice to get the mail off of the first ships to arrive in early June, but they're very high sea ice concentrations persisting, better than 50% persisting into early June. That just has not happened in the modern era. This complete segregation of these outlier events here is really telling. This was the throwback to an earlier era that we just don't get anymore, even though there's not a lot of difference here in the averages. These extreme events are really telling an important tale, I think. So that is what I have for you, just a summary of our paper. So during the 1990 to 2020 period, all of the events that had community scale impacts occurred with little or no sea ice. You already know that. On average, the sea ice season is now 1 month shorter than it was in 1980, and that is pretty much evenly split between the fall and the spring. But the changes in the fall are more consistent. And I think this is really important for planning, for adaptation. The risk of coastal flooding, the reasonable risk, just based on late 20th century, early 21st century, has already extended in the fall, in November, about 10 days. And this is potentially really critical, of course. I fear that MURBAC gave state and federal agencies a false sense of what they can do. MURBAC, of course, occurred in September. There's still plenty of daylight. It wasn't freezing yet. What happens if there's a MURBAC scale event in, the 1st of December, when the very short daylight, when temperatures are virtually guaranteed to fall way below freezing after such a storm? That is going to be a whole different kind of response needed than we saw in MURBAC. The response was, better than we'd seen, but it was almost under optimum conditions. And if we get that kind of event much later in the season, even into December, that is going to be very difficult to work with. That is what I have for you. Thanks very much, Gay, having me back again on Straight Science, and for Northwest Campus for hosting Straight Science for years now. I did put up the references here to our 2 papers that look specifically at Nome and use the nugget as the lived experience source for this kind of information, my contact info. So,
Awesome. Thank you, Rick. And it's always a treat to get you on at Straight Science. You're always so interesting talking about and your knowledge of the region. So this is the time for Straight Science while you're thinking of your questions to throw some love in the chat for Rick. And hi, Jenny. I haven't seen you in a while, so thank you. That's nice to see you here. And I hope all is well. So this is a chance to throw some love at the public speaker, which is Rick Thoman. He's taken time out of his evening to get us more information on what he's found regarding the timing of the ice and the impacts. And I've got a question too. And let him know that it's never easy being a public speaker. And thank you so much. So we'll open it up to questions. Any questions? You can raise your hand. And I believe we have a caller online. Let me double check. We did. And callers, nope, they're off. But callers always have the, it's never easy to be a caller on Straight Science. You can't unmute your whatever. You can't just show yourself. So I guess they are gone. And I don't see any questions. So my question, Rick, you just got to it as you were finishing up. So I was thinking we had in February, I think it was 2017, up by Diomede. Diomede was iced in, but with pretty lousy ice. And there are these very dramatic pictures, and maybe people from the region would recognize those. It was documented. February is supposed to be our coldest month, and this was in the strait where it's very narrow, and the ice had been set in. And I think the winds got to, I want to say 60 knots or 60 miles an hour, maybe. And all of a sudden, that sea ice, which was in a weakened condition from warmer waters, I believe, it started to break up, and then it started to chunk up into these rather large, very heavy, dense chunks of ice. And then the waves started out of the southwest and started throwing in those big rollers. They were just loaded with like jumbling large rocks that were then, but it was of ice, and they were then thrown ashore. If you remember those very dramatic and shocking images as the ice, which had never let go in February, was letting go and throwing itself at Diomede. I think they lost power, and they almost lost a person with all the excitement trying to get the boats out of the way and all that. But no injuries at that time were noted, and everybody was okay. But that's what I was thinking. I was going to ask, and you sort of brought that up. Is that, I mean, do we know, I guess we're not ready at the emergency level, how to forecast that, or would we? Because I've only seen that one time in that February storm, and I kind of can't imagine what that would look like if something came in like that from the southwest to Nome, where we don't have the advantage of height, to move things up really quickly out of harm's way down on the beach. But do we, I mean, do we know the likelihood of that? Or has there been some other incident where we've seen that other than that 2017 February drama of Diomede, just the ice just turned on them?
Yeah, that's a great question, Gay. Yeah, that Valentine's Day 2018 Diomede was not
2018.
what it was supposed to be, right? I mean, really,
Shocking.
really, house-sized chunks of ice on the helipad, water up there, that's just, it wasn't that long ago. Of course, on Valentine's Day at Diomede, you had the runway, the fixed wing aircraft runway out on the ice. What would happen if for a similar event in Nome? A big difference for Nome and the southern Seward Peninsula coast is, of course, that some version of south winds is going to blow ice to the coast, and then it gets stopped. Unlike at Diomede, of course, where south wind, the ice can blow through the gap there between the islands and keep on going. The land, in that sense, for Nome, would provide a stop, a barrier for the ice movement. So to get significant flooding in Nome in that time of year, you would really have to have more or less no ice to the south or southwest of Nome, so that it couldn't get piled up on the coast. We haven't quite seen that yet. That could happen one day, but we haven't seen that yet. Obviously, we have seen repeatedly, unfortunately, in other places like the North Shore of St. Lawrence Island, the north side of the Seward Peninsula, Shishmaref, times when south winds have blown the ice out. Being on the south coast, Nome and all the communities along the Seward Peninsula, South Seward Peninsula coast have a little bit better advantage there in the land acts as a stop. And so even if there's not a lot of ice, it'll get pushed up against the land and help to be a barrier to the worst of the high water that certainly could, and we've seen cases of it develop in midwinter.
I was trying to find a picture so I could show the audience what we're talking about. And maybe if someone asks a question, I can zip off and try to dig there. The other question that made me prompt with your answer was, we do worry about EVUs. So that's when IVU, that's when the ice is just driven ashore on the wind. And I kind of wonder if that's how it'll really look. It won't be these big rollers necessarily, but if we get so much thin, and then it'll just come right up and we have that gentle slope to the beach. And I've seen EVUs and it is dramatic when they get going, and in minutes you can have huge piles of ice. So anyway, it gives me something to think about that I hadn't thought about for here necessarily.
Yeah, that's an of course, as you point out, Gay, EVUs have occurred in Nome, where ice got shoved up by the water. EVUs are kind of interesting in the sense that if the ice is too thick, it's going to be stable at the shore and the water will come up, but the ice won't break. If it's too thin, then the ice will easily break up, but it will be, mechanically broken further as the water rises and waves work through that. So there's a sweet spot. I don't know exactly what it is, but there's a sweet spot. Not too thin, not too thick. That is prime for
That's right.
EVUs. But we have seen that in Nome. We've seen it at Kotzebue. We've seen it at Utqiagvik, of course. Any place can potentially see that, but there is a kind of a best thickness, best ice quality for EVUs to get going, and as a result, in most places they're pretty uncommon.
Goldilocks ice.
Yeah.
It looks like we have a question from Jenny in the chat. Go ahead, Jenny.
Oh, yeah. Hi, guys. Good to see you. It's been a while. Thank you, Gay, and thank you, Rick, for a really interesting presentation, particularly pertaining to all those great archives at the Nome Nugget, which I'm very familiar with. And I have a question just about that process. How long it took, what was the kind of strategy, because those books are very thick and it must have taken a lot of time to go through all of that material. Thanks.
Yeah, thanks for the question, Jenny. So excellent question, and Nathan Kettle, who is the lead author on our paper here, he is a social scientist by training, and so he knows the right way to do this. So this paper actually built on our 2020 paper, where basically we worked to identify keywords that we were looking for in the search. This was made easier in the sense that, is it 2010 or so? There's the Nome Nugget is online and archived online, so it can be electronically searched. Before that, though, for the stuff pre whatever 2010 or so that's not digital, we had a couple of people in that 2020 paper that systematically went through the archive looking for keywords that are in the list, and then did they find the keywords? Of course, oftentimes the keywords referred to some event not in Nome, like might have been in California or something. So there's a whole process to winnow those down to things that were specific to Nome, had the keywords, so that we weren't. The idea, of course, was to make this replicable. So if you followed our list, you could get the same results. So we built on that 2020 process, and then extended it a little bit then. And it, like I said, with the digital searching available for optical character recognition, that made that part of it much quicker. But the 1990 to 2010 was very labor and intensive, to say the least.
All right. I can't seem to find that picture. Did that help, Jenny?
Yeah, very interesting, and I'm not surprised. I envision people sitting in that newsroom just poring over those pages. So thank you.
All right. Any other questions? Well, I've got lots of questions. So for the other one that I noted was, if we're losing a month of sea ice time, so what was it, 2 weeks in the fall, basically 15 days later on average, right? It's being formed, and then it's 16 days earlier. I'm just wondering, with your paper like that, I wonder if that can get picked up or utilized by some of our federal marine mammal or seabird biologists, because I think they would. That's a good thing that you have that they can grab that and say, here's the numbers. What does this mean for? Because there are marine resources that are utilizing sea ice as part of their warp and weave of life. We could maybe start to look at what are the shifts as well. That's a lot. I mean, if you're supposed to be pupping at a certain time and your window's pretty short, like bearded seals, the pupping season isn't very long. And once they get going, it's like all the bearded seals are here. And they have a very short maintenance, mother pup maintenance. It's about 10 days to 2 weeks. That's it. You lie down on the ice next to your pup and it suckles you until it's fat and you're thin, and then you're gone. So I'm just trying to think if that's not insignificant. And so thank you for this. It makes me think about how this kind of information could be used.
Yeah, like I said, hopefully this, again, there's very little of this that's going to be new to Nomites, but having this in a paper means that its potential uses, whether it's Nome planning, or if there's biological implications. I think Zav Gravinsky, one of our folks on our author team who did a lot of this data processing, he did all this data processing that I've shown here. He downloaded. He's got all the digital files, since January 1979 for this. It would be possible. I mean, it's a big data crunching exercise, but you could develop this kind of statistic, at those 15 by 15 square mile grid boxes. You could show the change in, say, the total length season, grid box by grid box. That's certainly within the realm of doability, and maybe this is an inspiration for that kind of more spatial work. Because our focus here was particularly on coastal flood, this was and sea ice and how those two interact. That's why we chose this. But there's a lot of things we can do with that sea ice information.
Thank you. Honestly, I've got one more question, but I'll hold off. None. All right. So the other one of your first graphs. I was sort of looking at that. You had a 1990, you broke it down. 2004 was kind of the year you cut it there. It was 1992 to 2004 in the storms there.
Oh,
Yep, the one where you had there. So 1992 to 2004, there was only one. So that's 12 years. That was only one storm to meet your criteria. But from 2004 to 2015, there were 7 storms. And that was 11 years. So something close to that. So there were so many more storms in that later period that were impactful. Is that because that's the whole point, right? That there was no ice, that really shows the season has shifted? Or
so
is it
so
more frequent storms?
you know, this paper here, and so this paper here, the periodicity storm through the 90s, and then Carol's, you know, the big storms. If you look at the dates in this list, they're very episodic. They're really chunked up. So nothing made Carol's big storm list here between 1913 and 1937, and then there's this whole slug in the 1937 to 1946, and then there's this long gap 46 to the great 1974
Wow.
storm. Now, of
Okay.
course, what happened between 1946 and 1974 is, of course, the seawall was built. So maybe that played a role too. But then again, in Carol's list here, yeah, so 74 to 92, nothing made the list there. And then nothing here on her big storm list for 12 years there. So to some extent, it's because it's episodic, because so many pieces of the puzzle have to come together to create coastal flooding. Like the airport wind study showed us, the winds are not alone enough. A lot of other factors have to come in, and so you know this is I thought this was really interesting, and actually I did a double take here. So look at 2004 here. So there's this event here on October 11th, which I'm sure no one remembers now because it was overtaken a week later by the big storm, this big storm in October. But it was preceded, this is kind of the ambient condition, you know, setting the stage, elevating the Bering Sea ocean level overall. Similarly, in the 2013, which is the 2011 is the Bering Sea superstorm. 2013 storm was maybe more impactful in other parts of Norton Sound. This is the one that so severely damaged Kotlik, but there were impacts in Nome. But that was a series of storms, and that shows up here in the Nugget reporting with one here is November 6, 7, and 8, and then a week later, the last storm in the series produced damage on the Council Road. So really quite interesting here. Same thing we see here in the 2015. Same month, we're obviously in a stormy pattern. Some of these were bigger than others, but it really highlights that the episodic nature of all this.
So it's not that the storm frequency, and bear with me, I'm just sort of slow on the dryer, but it's not that the storm frequency has increased. It's just that storms are storm climate. I don't know what you'd call it. Storm.
These high impact events, you know, they're in the historical record, there are these long periods when we don't get all the pieces to come together. So you go 20 years without a major community scale impact. And then you get a bunch of these, you know, in short order, you know, back to back. You know, these are, in some sense, I would say these are not independent events because the October 2004, November 2013, November 2015, we're in a stormy pattern. Things are churned up, water levels are elevated. And so it's not, from a meteorological perspective, it's not surprising to see this kind of clumping.
Okay. All right. That helps. I think we could use a break in the Bering Strait region, just events in general. I think our motto is just be happy because it can always get worse at the moment. But thank you very much. That explains that. Any other questions? Comments? Others? We are over the 7:30 mark. So I will say here that on Straight Science will be next Wednesday, the evening of March 19th, and it will be Sarah Fowle and her team from the University of Alaska Fairbanks Department of Sciences. And this is a rest of the story, her Straight Science. In 2013, in 2023, her team was set off on a ship to take sediment cores below the ocean to find out what was, and Rick, you might be interested to find out what was the Bering land bridge. What was it like? Was it grazing plains? Was it a mucky bog? What was I guess the climate at that point? What was it like in their sediment cores as they went down through time through the bottom of the ocean, which was once above the ocean? And she's going to give us the results of her work that she's done. So that'll be pretty interesting. And her first version, when they set off, that is archived on the YouTube. But she will come back and tell us the whole story, including her results. So I'm excited to find out what they found from those underwater sediment cores that will show us many years ago what the terrain and maybe, I guess, the climate too, Rick, would that be, do you know if Sarah Fowle's work up there on?
So yeah, so what we can infer from those sediment cores, there's lots of stuff embedded in that stuff at the bottom of the ocean.
Yeah.
Spruce tree twigs, pollen. If I remember correctly, they even came up with a handful of animal remains as well, bones
Holy cow.
or mammoth tusks or something, or pieces.
Wow. Well, tune in next week and we'll hear the whole story. So thank you for that, Rick. And it sounds very interesting. And she was nice enough to give us a forward look at her project. And now she's coming back to tell us what she found and what our land bridge looked like climate-wise and terrain, vegetation-wise, many years ago. With that, thank you all so much for coming. Rick, if you could stay on for 1 sec.
Yep.
And that's it. Thank you, everybody. Have a good night.